Hi everyone. So today we're going to do examples. And so I put up 3 examples right here that you can try working through on your own. I'm going to start this one by subtracting 4 from both sides, and that's totally legal. So you can still do the things that you would have normally done in just normal world, as long as you do it to both sides, right? So the thing that I was trying to talk about before was what's special is I could add 3 onto both sides or something, and that would be fine, because 3 is 0. I could add 3 to just one side or the other side or something. Okay, so I just want to start with that. Let me give you another good look at the examples. You can try them on your own, see how far you get, and right about now I'm going to start doing the answers. Okay, so like I promised, I'm going to start with this, i.e. is this true, right? Where is 6 equivalent to 0 mod 3? Question mark. Well, yes, 3 divides 6, so yes. Or the other way you could say it is 6 equals 2 times 3. You know, choose your poison. Pick your poison. But yes, it is true. So 10 is equivalent to 4 mod 3. Cool. All right, so number 2, we want to show 6n. Ooh, that's ugly. Show 6n is equivalent to n mod 5. Okay. All right, so let's start our proof. So first thing is maybe I want to minus the n on both sides. So maybe I say we note that 6n minus n equals 5n, and 5 divides 5n. So, oh, yeah, I guess that's just it. So we're just done. Therefore, here, maybe I'll write it like this. 5n is equivalent to 0 mod 5. So if we add n on both sides, we get, boom, roasted. Okay, number 3. And please, if this is taking longer than it's taking me, that's totally fine. I'm kind of speeding through them a bit. Yeah, and I've known this stuff for years now, and you're just learning it. So don't be hard on yourself. Okay, so number 3, prove for any integer n squared is equivalent to n mod 2. This actually can be extended. Another number theory thing. Okay, proof. So I'm gonna try to show you a different way of talking in a proof. So I don't think I've ever said this in this class. Take a generic n in the integers. So that's you like really making it specific. Oh, I'm not picking a particular one. I'm just taking any integer. Then, well, what do we know about integers? We could do the division lemma, but we know some nice things about an integer and its square, and we know that it maintains whether it's even or odd. So maybe I want to think about that. Then n is either even or odd. So as you've probably noticed, there was probably a bunch of different ways I could have started this problem. And so that's what I've always been trying to encourage you all about, is just because you don't do it the same way that I do it, or another instructor does it, doesn't mean that your way is wrong necessarily. There's usually a lot of ways to do any question. Okay. So maybe let's suppose first that n is even. Whoops. N even. Then n squared even, hence n squared minus n is an even minus an even, so it's even. And so the way to see this is you could write both of them as a multiple of 2, and then you can factor the 2 out, and then the subtraction of 2 integers is so it's even. Okay. It being this thing. This means n squared minus n is divisible by 0. Nothing is divisible by 2. So n squared is equivalent, whoop, too many lines. It's equivalent to n. And so this is kind of the same thing I talked about before. So you could start it with this on this side and then just add n onto both sides. All right, so how about when n odd, okay? Then we know that n squared, odd. Now, here's the interesting part. N squared minus n is then even, since odd minus odd. So if you think about it, it's like, so let's say 2k plus 1 minus 2l plus 1. So those ones cancel each other out. Now you have a multiple of 2 again. Is even, okay? Therefore, as above, we get n squared is equivalent to n mod 2. Woohoo! Okay. As these are the two, so I'm trying to write it fancier. I sort of forgot for most of this in the middle. As these are the only two possible cases, we see squared is equivalent to n mod 2 for all n. Yay! Okay, sorry. So that, then it's since n generic. Then true for all n in the integer. There we go. Okay. All right. Okay, so here's our last two examples. You can pause and try them. I'm about to show you the answers now. Okay, so you'll notice I didn't really do a whole lot of examples of, well, I didn't do any examples of division lemma. You'll get a lot of practice with that. And I've noticed in my experience teaching this that people tend to have more problems with mod. So that's why I chose to do this, but okay. All right, so let's start out with what we already know. So if y is equal to 1 mod 6, then 6 divides y minus 1. Okay, well, what does that mean? i.e., there exists some integer, say k, such that y minus 1 equals 6k. All right, well, now let's think about x times y, I guess. Or x times y minus x, because we want to say that that's divisible by 6. X times y minus x equals, well, we can factor the x out. We get x times y minus 1. Well, that's going to be x times 6k. Okay, all right. All right, well, why don't we just move that stuff around? We have 6 times xk. Well, these are both integers, so the whole thing's an integer. Then 6 divides xy minus x. Woohoo! Boom, roasted. All right, on to the next one. Sorry, maybe I did that a little too fast. All right, let x and y be integers such that x and y are, neither of them are equivalent to. So this means not equivalent, just kind of like not equals, you know. So neither of them are equivalent to 0 mod 3. So now I want to prove that them multiplied together is not going to be 0 mod 3. So this might seem kind of weird because you might be thinking, Danica, you told us we weren't going to do any multiplication. And that's true. We're not going to do any multiplication inside of mod, but outside of mod. All right. Let's start. Or you could try it on your own. Okay. Note that if x or anyone, if they're not equivalent to 0 mod anything, like 0 mod 3, for example, then that means that 3 does not divide x minus 0. But what does that mean? That means that 3 does not divide x. Okay? Similarly, 3 does not divide y. Okay. All right, well, what do we know about things when the division doesn't work? We can use our division lemma, and then we can just say that the remainder is not 0. It has to be not 0. Okay? By the division lemma, I don't know if we're supposed to capitalize. All right, we may write, I don't know, you just make up whatever letters you want as long as you don't repeat anything. x equals 3k plus r, and y equals, let's say, 3j plus q, with r equals 1 or 2, and q equals 1 or 2. Okay, because those are our only options. It has to be strictly less than 3, but it also can't be 0 because 3 doesn't divide either of them. Okay? All right, so let's do some calculations. Then, so notice now I'm back into just like kind of normal math world, the math world that we've grown up knowing and loving. Okay, so we have this minus 3j plus q, 9kj plus 3kq plus 3jr plus rq. Woo! Okay. All right, so kind of weird. But what are we trying to focus on? Like, what's the important number here? Like, why? Okay, so sorry, I skipped a lot of stuff, didn't I? Skipped a lot of my thought process. So why did I pick 3? Well, that's my important number over here. So oftentimes when you're trying to figure out something with mod, in your division lemma, you're going to use 3 as like your divider thing, or as your m. Yeah, which was the second video, but okay. So we might want to be able to see, we want to show that xy also is not divisible by 3, okay? So I know if we snuck over into number theory, we could do a lot of things because 3 is a prime number. So that's fun. But let's do it this way with the division lemma. So if I wanted to apply the division lemma onto xy, but with what I already have, well, I could factor out a 3 out of everything. Because remember, that's our important number here. So that's who I want to see if xy is divisible by or not. And now I have this left over. So now this is my remainder for xy. I want to show, so let's talk about what we want. I want that rq, or the remainder, to not be 0, okay? Or else, then it would be true that x times y would be equivalent to 0 mod 3, okay? So I want to show that that's not possible. Okay. So let's see. Let's look at all of our possibilities. So in fact, without loss of generality, there's three options. Okay. So to not be 0 or a multiple of 3. Because then what would happen is maybe you could factor out a 3 here, and then our remainder is 0 because everything's factored out. So let's look at, so without loss of generality, which means it doesn't really matter if I say, so let me get into it. We have 3 cases. So 1, maybe both of them equal 1. Okay, then r times q equals 1. So 3 does not divide x times y. Good. Okay, 2, r could equal 2 and q equal 1. But notice this, I'm going to get the same result if I considered r equals 1 and q equals 2. Okay, so just one of them is equal to 2, the other one's equal to 1. Okay, rq, then that's going to equal 2. Okay, well, once again, that's not 0 or a multiple of 3, any multiple of 3. So 3 does not divide x times y. Okay, well, my last case is if they both equal 2. Okay, so then rq, okay, well, this is the weird one, isn't it? Okay, so, so why is this still okay? Why can we still prove that we're right about this? Well, what we can do is we can go up here and steal what we have and say, okay, x times y is equal to, so it's equal to 3 times 3jk plus rj plus kq plus, and now we have 4. So yeah, we could plug in a lot of stuff over here, but we don't really care right now. So if it's plus 4, is that an issue? I don't know. Let's see. Well, remember, our remainder has to be less than what we're dividing by, and what we're dividing by here is 3. Okay. So, well, we're trying to find the remainder of, you know what I mean. Okay, so we could split this into, so 4 is the same as 3 plus 1, so we could write that instead. 3 plus 1. Okay, all right, so then we combine these, plus 1, right? So this moves in. And then our remainder is 1. Okay, so then 3 does not divide xy in this scenario. All right, so now we get to say we covered all our cases. All right, we're all set. See you next time.